together and doing things like sort of projections, like health projections. So we would make health solutions and say that it stays within the healthy regime. You know, we're depleting our funds so fast. We are passing proposals so frequently. The sort of system is circulating so many times per period. We're talking about the things that talk about the holistic, in a holistic way. How fast are we getting donations relative to how fast are we issuing proposals? How large are the proposals? What is the, you know, involvement frequency of the, you know, of the tokens? Are people participating in most decisions or are very few? And like, again, the difference between this and just pure analytics is that what we're doing is taking not just the past data, but we're using it by taking the past and saying, given CAD and continue how they're currently going, where does that take us? And that's a sustainability framework as opposed to a purely backward facing, hey, we haven't died yet. This is saying how long going how we're going is okay. And ideally, that's sort of, you know, a long enough horizon. You push it out a couple months, you say, hey, cool, you know, everything's great as long as it continues how it is. And if you start to see that straying, that's the time that you draw attention and you sort of, you try to engage with your community to take action, make new proposals, make decisions to curtail the projection into an undesirable regime. But what I'm still talking about here is not yet system identification. System identification is a whole level above, because in that case, you take parameters of the CAD-CAD model and you machine learn them. In this case, we're keeping the CAD-CAD model as essentially a, you know, a static model in this sense of bring us. You still push the, like, how hard you're pushing on it. So, you know, the spring and mass bouncing back and forth. We have data about how people are pushing on it, so we can say if people keep pushing on it, where does the spring go? When you get to the later tranche, we're going to be taking that a step beyond and asking, what's the spring coefficient? What's the mass coefficient? So that's the big difference between CAD, the analytics version 1 and analytics version 2. Version 1, we have to get all of the piping together, which would make it possible. And version 2 levels up the quality of the AI by an order of magnitude. But the top of this funnel on the first one, though, is this going to be sort of then UX design. And that's going to have to do with these web apps. And actually, I think I've been trying to get Jeff involved with my discussions with Max, because Max is currently building the High5 prototype. You've seen the Lo-Fi prototype, right?
Yeah, you sent me an email with all the information on that. I had a look through it. It's been a little bit.
Since we're going to do a little bit of sharing here, just to kind of get people on the same page. But this is a Lo-Fi prototype from tab. Let's see. Layering.
I'm looking at.
I haven't shared it yet. I'm just trying to find it. I have way too many tabs open. So.
I'm looking at it on Jeff's.
I see. I have the digital twin thing pulled up here.
Yeah. So I'm pulling up. That's a spec. This is actually a specific demo. So let me just find it.
And is that digital twin a layer 2? Because the digital twin explanation is something I can really.
So digital twin, let's get to it. I want to talk about that specifically. I think we can use it in both layers. Let me just start with this first one. Okay, so this thing that I'm sharing to you now, this is a web app demo. So have you seen this, Griff?
Yeah.
Okay. So I'll be quick about it then.
I think you talked about it when we were doing the Binance fellowship thing. The POC.
But this is what I'm. So this is the Lo-Fi prototype. So right now, this thing, we took a CAD model that we have, the three-sided market, which is one that we have a whole CAD model of. It's this kind, right? It's all Python, does its thing. But instead of having this, Jupyter notebook for these analyses, Andrew, who's one of our data scientists and economists, made this. Sorry, I don't know. You can see my screen when I change, or is it only the same kit?
Oh, we see it.
Okay, cool. Okay, so here I ran an experiment to see what would happen. I actually saturated it. So, this is, if I wanted to reset this to its original parameters, I would set that, and I would hit run, and it would run, and God damn it, my Wi-Fi is not that great, so let me give it a second. Anyway, I took a couple of the parameters, or I should say Andrew took a couple of the parameters, and he factored them out and put them in there. You can just do this little Q&A thing where you're like, okay, well, I pick some numbers, and then I see what happens. And this actually runs an experiment, not this one, not just a single run. It's looking at what happens with different reinvestment rates. So this particular system accumulates capital differently depending on how much of the capital it reinvests. It's not a particularly sophisticated model. It's a template. So you have to obviously play with it to fit a specific system. But here we're showing this mainly the difference between the fiat and token reserve as a function of whether they're taking their fiat and using it to distribute more rewards to the sort of community in this network. And you see the wealth accumulation is much lower if it caps off. In this purple case, it's the case with the largest reinvestment rate. So reinvestment rate grows fastest, means the capital accumulation tables off. And this is basically just we're examining policies when the system get rich. Its job isn't to get rich, its job is to empower the system. So we're examining what happens when we take the profits and reintroduce them into the ecosystem. And this is well, it's not fully run, but this is just an example of a lo-fi one. And it's on a really cheap server, and it's just there so that we can do demos.
Mm-hmm.
But we're already starting to use things like this to help our clients, because the truth is those Jupyter notebooks are not useful to non-technical and non-data science end users, right? So what we're doing with the thing that Jeff has up, and I'll stop sharing this and I'll pull that up now to talk about it, is that we are, and this is us getting out ahead of this stuff, right? Like we're doing it because our clients need it, and we're doing it because our project, but we're working with Max. Let's see, let me make sure I have it. We're working with Max to get built this extra layer of web app. So this is what we're calling the High5 Prototype, because again, it's still just going to be that same model that I just showed you, the three-sided, but we're going to be able to fork it and use it to wrap other models, right? Like for example, I want to wrap the conviction model in the same thing. That's part of the reason I've been working hard to get Ravi involved, because I don't have time to keep pushing that model, but I have time to continue to train someone and help someone do it. And so I had a great call with him today. I'm super excited. Send him more material. I think he's going to be awesome. He really gets it. But the key here is that, you know, even in my own team, I'm not the primary modeler. I do the prototyping and the designing, and then I hand it off. And so the key here is to get him rolling so that he understands it deeply enough, you know, for the future, get the prototype out. And what I'm actually saying is that the models that we use for the analytics dashboards are going to contain some version of that model, which is modified to match the commons itself. So that one has the bonding curve, and it has the conviction voting. It has a lot in it, but it's actually easier probably to cut stuff out of it to make a version of a CAD model that matches a specific implementation than it would be for me to then add it. It's going to be easier for us to scope it down than scope it up at this stage. So that's why I went ahead and tried to prototype the whole thing.
Yeah, I think we'll probably want to start with the token bonding curve, as that's where we start anyway, right?
Yeah, but the thing is, the token bonding curve is not a system. You have to attach the token bonding curve to something. So a lot of what I put there, whether we use conviction or voting or not, is going to be necessary, because that model contains things like private signals for individual preferences. It doesn't matter whether they're making box decisions or conviction voting system decisions. You can't actually model a human's decision making if you can't generate their private preferences from which they make decisions. So but I already wrote that part, so you can use it. In the real world, we don't know people's private signals, so our real models are going to have to essentially abstract some of that away. We're going to be looking at, you know, possibly estimates of the distributions of people's preferences, because the voting system itself is actually an estimate of the distribution of preferences. You see what I mean? And so we're actually dealing with something which is a dynamic, a voting process, a decision-making process is actually a dynamic estimation process. You are creating a system that's job is to estimate the preference and execute it.
Okay.
regardless of what algorithm, whether it's a time box voting or not, the purpose of a voting system is to estimate the collective preference and execute it.
Yes. So.
And so we have a baseline model for that now, and we can modify it as needed. And I'm excited about his involvement. I think it's going to be important to get Spanette and/or Will involved, because I don't think Ravi's a developer. He's more of an engineer, but I'm pretty optimistic about his ability to learn and manage CAD.
Yeah.
So from an analytics perspective, coming back then, what I view the common stack analytics are going to be a version of what I'm showing you right now, but the top level this UX funnel that says exposes complexity slowly. This is Mac's territory. So he's been researching this a little bit. He's got a lot of opinions. It's one of the reasons I'm excited. So I'm actually currently paying Magic Power to work on this with me. So so that's not just a like, hey, Max, do stuff for me. Obviously, there's going to be common stack specific stuff in the future, and most likely the way I see this happening is that when we get to that level, one of my subcontractors, him, is the only one, but they're very good with simple UX for complex phenomena. And so we'll have 3 layers basically. Data infrastructure, which is the stuff that we talked about at the beginning, for which I think there are many potential subcontractors in the community. Then we're going to have the AI and sort of CAD layer, which is inherently going to be block science driven just out of necessity. And then there's going to be UX and sort of like simplifying complex concepts for the end user, which is something that I very much trust Max and Magic Powered for. So that work is going to end up being, we'll end up taking that budget and distributing it across the labor required to execute. But this is also the reason why I wasn't willing to shirk much on the cost there, because doing it right is actually not just like some block explorer. It's a 3-level problem, from data infrastructure to AI to UX.
Wait, so AI is coming in layer 2?
So AI as a term here can start produced with data. So this way. Data infrastructure is just analytics. It's raw. It's let me give you statistics. When you take the statistics and you take models and you use those models to algorithmically improve your interpretation or your understanding of the data, that's AI. Like, full stop. That is it's an entire field in its own right, and you can do it badly. And if you do it badly, you make things worse, not better. So the moment that you take the idea that there's a CAD model, like CAD is an AI discipline. So, or it's in the AI class, not in the data and like the pure data plumbing class.
Yeah.
The are 3 layers. One is data collection and curation and sort of staging and collecting and formatting and cleaning and all of that, right? That's what we talked about at the beginning. The second thing is, once you have clean data, what do I do with it? What do I infer from it? And when you're talking about systems, holistic systems, statistics are actually not very good. They tend to tell you things that may or may not be misleading, and it's hard to tell unless you have a lot of expertise. So you embed the expertise in the AI layer. The people who helped design the systems, the people who are most familiar with them, the people who are have been working with them, create a layer, which I'm calling the AI layer, which is helping interpret the data. And that's still just data in, data out. And the last layer is then, given that, sort of making it available to the end user and helping them understand. And that's the UX layer. And that's one the design the case for how the user engages with the data. So this is the best practice for turning data into information for the purpose of supporting the community or the mahoots or the whomever. But the point is that if you want data to not just be some noise that you can knee-jerk against and do stupid stuff, you need to take it all the way from its raw form to its clean form to its reduced form to its inferred form to its presented low complexity decision support form. And step over step over step, that's the process.
And where does the digital twin machine learning piece come from?
That's in the AI layer. And so it's present.
But it's probably going to be more in the second like round of like the fifth iteration?
You can use the term in both, but the difference is in one, the first release, in the sense that you've built a digital twin and you feed it with state data. In the second release, you've made the digital twin parameterized, and you have a second layer of machine learning that learns the digital twin. So in a sense, if we go back to our circuits or model, I have a circuit, it's got a bunch of capacitors and resistors and inductors in it, right? Suppose you set the numbers for all those capacitors, inductors, and resistors, so you know the circuit, okay? Now, if I have real data about the input signal on the circuit, meaning the voltage, then I can use the fact that I know the circuit to tell me about voltages at other points on the circuit, right? You with me?
Sure.
You can.
Yeah.
So simply put, if I have a circuit and I know the capacitors, the resistors, and the inductors, and I have a couple places where the outside world touches my circuit, and I measure the signal coming in, given that I know the circuit, then I can compute not only the current, but even project and estimate the future values of the circuit at other points. That's in that circuit model is a digital twin. At this point, this is still just what I described for the first phase, because there's not a machine learning of the circuit. There's just, we say we know the circuit. Do you see what I'm saying? We measure real.
But you're also saying that you can predict the future to a point.
You can't. Well, yes, to a point. So what you're doing is predicting the future by predicting the inputs. You're looking at the past inputs, and you're saying, cool, I have a model of my past. And now I'm going to say, instead of linearly projecting into the future, I'm going to predict my inputs based on what I've seen, and then I'm going to project it through. And this is giving you a better prediction of the future. It doesn't give you a perfect one, but it gives you a better one than if you didn't know the circuit at all.
Yeah. Okay.
Yeah.
Makes sense. Yeah.
Now that is just like relatively straightforward, like systems and signals. You have observable signals, you measure them, you have a system, you push the observed signal through the system, you get a prediction. This is like crazy old school engineering at that point. But it's also best practices for modeling systems when you know the system. Like, just regardless of whether it's engineering or whether it's crypto, the whole point is that you know how the system behaves. So you up to a point, therefore you can get better predictions than if you just pretended you didn't know.
So would you say that the next layer, I'm calling this layer 2.5 because it's to separate the iterations out.
Right.
Would 2.5 would be like you take the digital twin and you run machine learning algorithms and you can kind of determine the health of the system, or like the probability that the inputs.
So now you're kind of misusing the machine learning concept there then. So the health of the system is not a machine learned thing. The health of the system is a consequence of a machine there's, I guess let's go three things. There's the signals, there's the system, and then there's metrics.
Yeah.
All right. And in fact, actually, I have a different thing I can show you because I got permission from Thibaut to share this. So I have another document that I can share because I'm working on Fairmint on continuous orgs. And I'm not supposed to distribute these, but I'm allowed to share them with people to talk about systems. So, and in the future, they'll probably get shared, but he's like, who's standing his and mine trying to get them explained. It's amazing, actually, how much of the difficulty comes from just people's lack of understanding creating extra work. And if they're not people who need to understand, then it ends up actually being waste work. So this is a model of the continuous organization system as a what I'm calling a sort of economic circuit or a flow diagram. You guys have seen my flow diagrams for Common Stack, so this shouldn't be too scary. I'll give you guys a minute to ingest this because this is the system, and I'm going to show you a CAD diagram for this system. The nuts and bolts of it is that there's this special bonding curve in the middle that Thibaut designed that has a special character in that not all of the money goes into the bonding curve. Some of it goes directly into operating fiat. It's a bit like the inverse of the common stack one, because in the common stack one, money comes out when you sell, and in the continuous organizations one, money comes out when you buy.
Mm-hmm.
So like any questions, we've got a primary market, which is the bonding curve, a secondary market that is essentially Uniswap style, and we have a business operation that basically converts spend into future revenue.
Yeah.
Cool. So this is the continuous organizations model. He's got this sponsored burn chain here, which is one of the things that we're analyzing. There are going to be legal commitments about the circumstances under which a Sea Org is required to use this mechanism and this mechanism.
Yeah.
So leaving that aside, that's a system that we're working on. It's one of our current projects.
He's going to make this a full-on security, right? Like this is a...
Yes.
Yeah.
It's an equity. This is literally an equity.
Yeah.
But he's got legal work in the works too. But we're building the digital twin of this right now. So like we're actually building a product which is digital twin to go alongside of their continuous organization in order to allow them to help assess the continuous organizations, the investors to make decisions, and to help them do projections to help them onboard continuous organizations, like help them understand how to configure a new continuous organization.
Mm-hmm.
But this is like an ongoing project with great people. So
it'll make doing the stuff for the common stack way better.
And I mean, that's one of the reasons why he's excited about Common Stack, and he's been following up and asking questions about it because there's a lot of synergy. They're different because this is an equity of a startup, basically, which is a slightly different business model. So the ontology is different. So the design is different.
Yeah, for sure. Different users, different systems. I mean, there's a centralized party here that gets fiat. I mean, that's wild.
Yeah, but the point is, it's still a really powerful use of automation technology to make this engineerable.
Yeah.
Okay, so in this case, got a handful of, so this is a CAD system definition, which eventually we'll have to have for helping specify out the CAD models for Common Stack, but right now it's not an active project, so we don't have the resources to spend on it. This is the behaviors and mechanism. So top layer is behavior, so that's action. Mechanism is consequence of action. Yellow here, these are data feeds that don't exist. So we have statistical models that allow us to ask questions. So when you don't have a live system yet, you don't have real data. You have to basically make some assumptions and synthesize data. You say, okay, what if there's speculative pressure? What's the adoption process? Like what's happening in the world? Because we don't have the real world data, we have to, synthesize the world part.
Yeah.
So that's yellow, exogenous process.
And how does this is the digital twin for the analytics. This is like the start of it, basically.
This is a diagram. Yeah, this is the diagram of the digital twin. The digital twin is a mathematical representation of that system, and it is coded in CAD that allows us to run simulations, allows us to build in the future to have a web app running. But I'm trying to go through what you're asking about the digital twins. I'm like showing you what a digital twin is.
Yeah, I see this, but I don't want to go too deep into the details of their system just for our own time, because it'd be nice to have some time to go into sync mode. And we only have 20 minutes left.
Okay, so I need at least 5 more minutes, though, because I'm trying to get to explain how the data integrates with digital twins. Okay. Because the point of this wasn't just to go over their system. The point of this is for you to understand how a digital twin and a data feed come together to result in health metrics.
Okay.
Okay, so one, it doesn't all fit on the screen, but you'll notice there are metrics on the bottom. So we got to work our way from the top to the bottom. So top is behavior. The second role is consequence of behavior. There's 3 categories of behavior. One is the outside world, the environmental processes that are not really under the system's control. They're just observed. Price spikes, adoption. You can model these things intrinsically, but for now, they're the environment. Then there's this internal decision-making processes. In their system, as you mentioned, is security. There's 2 kinds of actors that matter for the system. There's the investor role, which is people who are buying on the primary market, they're buying the equity from the bonding curve itself, and the trader role, which is people who are, they're not minting and burning, they're trading with each other. Mind you, technically these can be the same group of people, but that's just, you know, one agent fulfilling both roles, so that we can characterize the roles clearly in terms of the mechanisms that they act upon and the states that they change. And the last group are things that are invisible by either legal or smart contracts, meaning there's a parameter here, theta, which share of the funds goes to the operating capital. There's a buy commitment, which are the rules under which you have to use. There's a buy mechanism that was in that first diagram, and there's a burn commitment. Again, the rules that state the conditions under which the Sea Org must use the burn mechanism. And there's a closeout here, because the continuous organization can meet a set of conditions at which it kind of closes out and pays out all its investors. So these are the systemic designed policies. So they're automatic behavior. This is free. So we've got environmental behavior, we've got user behavior, and we've got automatic behavior. That's why there are 3 swim lanes. Those things interact through a set of mechanisms who are essentially deterministic. They're actually totally deterministic, but only as a consequence of non-deterministic behavior. So you're basically taking inputs that are not given, mapped through processes that for any set of inputs are given. And that changes the system state, which is what this states layer is. The states layer is the stuff that you have data about. So when we're getting real data, we're trying to conform data models. When I was saying we blow out the data as best we can, what we're going to end up doing is then creating another second data model that matches this as best as possible. You can use estimators to estimate unknown states. You have to basically, again, solve this sort of an AI layer problem, which says, how do I take the data that I have observed and use it to match it up with the data that which is like required by the digital twin. And that, in turn, how you then can compute these health metrics. Because even if you're not running the whole thing, you can see clearly there's a direct mathematical relationship between the states and the metrics. And what you do when you run it forward is look at how the system evolves, and then you can continue to measure how the health metrics evolve. And that's how you get bands and projections on whether the system is not only currently healthy or whether it is staying healthy. And if it's not staying healthy, you have to revisit things like influencing different behavior or potentially changing parameters or like submitting proposals to change these policies in the upper right. That's how you keep the system healthy. Does that make sense? So this is layer 1, where we haven't tried to actually machine learn the model yet. All we've done is just combine it with data. That's where we want to be. And that's the thing that we're working hard on right now. We're trying to get better and better at this so we can do it faster. We can do it, but it's still a lot of work. And so, you know, month over month, we try to make this easier and easier, because by the time we get to doing the, you know, level 4 common stack, like if we had to do level 4 common stack now we wouldn't even be able to do it for the price that you put in that schedule, because it's too much work. But by the time we get there, the idea is that we'll be able to subcontract the data infrastructure layer, we'll be able to do the AI layer, and we'll be able to subcontract the UI layer and get it done. Yeah.
So I'm still missing that final leap on how to describe, because this is the sexy piece, okay? Being able to say we will use machine learning on the digital twin to...
Okay, so can I go back to the circuits example then? Because I think now that we understand that this is a business logic circuit. So this is why I call this a business logic circuit. And it's a reason why I'm going to go back to circuits, because they're the things where this stuff is easier to explain. Yeah. In my circuit example, remember how I said we knew that the capacitor and the resistor and the, you know, whatever were there? And that we are saying that we knew what the capacitances were and the resistances were? When you really use machine learning, you're doing a thing called system identification to actively learn the capacitances and the resistances. So you know the shape of the circuit, but you relax your estimation that you know C and that you know R, and you use machine learning to continually update your belief slowly of what those are. And that gives you an even better representation of your digital twin, because you went from what would be like a batch learned sort of like, okay, here's what we think it is based on our last sort of update, to something that's able to adaptively sort of estimate itself. And that's really cool. But that's actually even currently beyond data science best practices. That's robotics best practices. And we want to bring that to this, but we can only do it if we do the other one first.
So we're assuming that this, like using this circuit analogy, this circuit is continuously updating in time, and that's why we need to use machine learning to continually estimate
the state. We have to separate the notion of the circuit state and the circuit. So the circuit, if you know the circuit and you know the capacitances and the resistances and everything, then as the currents and the voltages are changing, the circuit state is changing. But you are not changing the capacitances and the resistances, right? That's level one. We just say, here's the circuit. This is what we say it is, but we're still learning a ton because it's a circuit. It has living parts, and as the voltages and the currents change together based on the circuit, we know a lot more about how healthy the circuit is, because we can infer things about the voltage over here because of the current over there. You see what I mean?
Yeah.
Now, what I'm saying is that when you take it to the next level, you do this. I'm still doing that, but on a slower time scale. I'm continuing to update my best belief about what the capacitances are, what the resistances are. So it's a multi-time scale learning effort. And that's why I'm saying that this is actually not even best practices in data science yet. This is best practices in robotics, because in data science, you don't generally have digital twins. Historically, you require a differential equation for what I'm describing to make sense. And what CAD-CAD is differential equations for business systems. So you can't have system ID until you have differential equations. And so data science world is missing that. And so we're actually really trying to push the envelope here when we say, hey, we're going to take it from that first level where we have a digital twin, which is still very much a like top-notch, sort of best practices kind of analytics tool. But we're trying to say, we have CAD, we can even go another step further and apply the system identification technique, which is closely related to autoregressors. It's related to reinforcement learning. Now, the problem with reinforcement learning as it's currently thrown around is that people don't really understand how it works, and as a result, it's sort of used poorly, for lack of a better term.
And this is the thing, we don't know anything about that. We don't.
Right. And I don't want to try to explain it, because the amount of work that's required, like you're talking about things that, this goes back to my point about like being afraid of bullshit territory, because like, knowing what to do and knowing how to do it when we get there is way different than investing lots of energy trying to explain it to people. I don't want to. I just want to do it right when we get there.
We don't need to explain it in detail, but we really just need to know what we can't say. And it sounds like we can't say integrating machine learning into the digital twin to estimate the current health of the system.
You can say that for the second one, but my problem is that I don't know if you can explain it beyond that. I mean, the issue comes down to like it really, honestly, the answer comes down to how comfortable Jeff is narratively fielding the questions that follow, because it will be inappropriate to try to technically field those questions, because ultimately they would get us down a rabbit hole we don't want to go down. But the short answer is essentially that circuits description that I just gave you is a totally valid and correct way to describe it. It is in version 1. We're saying we figure out our best understanding of what the circuit is, and we use the understanding of the circuit and the knowledge of time varying voltages and in currents to better understand how healthy the circuit is overall with respect to some metrics that we define, which might be, maybe our metric is like, the total current across this one resistor is like the thing that really matters. But we can only really know that if we know the circuit, because it's not like that's the thing that's driving the circuit. The circuit drives a bunch of voltage or else. If we care about the current across this one resistor, then we have to have the circuit model in order to track that health metric. You see what I mean?
So, yes. So is the health metric actually determined by the machine learning?
No, the health metric is determined by like actually understanding the system. So let's be very clear. Metrics, machine learning,
by layer 2, not 2.5.
So machine learning, don't talk about it in layer 1. Or in 2. Talk about it in 2.5.
Yeah.
Second of all, machine learning, very badly used normally. I cannot express this enough. That 99.9% of applications of machine learning that I've come across in the general public, like not general public, but in the practice space even, are like less than 20% effective. Because the issue is that they only tell you about the past if you don't understand the system you're applying them in. And most people skip over you understand the system you're applying them in. So our version 1 says we're focused on understanding the system itself using real data and using these models that are representative of the real system. Because it's a crypto system, we know that it has to behave in certain ways. It has these circuit-like properties because it can't violate certain energy conservation or constraints, right? It has hard-coded rules like circuits that can't be broken. And as a result, we can treat them like circuits in the sense that we know a lot about them. And so we want to take real data, which is of the type voltages and currents, which is this, again, this activity behavior data, which is coming from the outside world and we don't totally control. And we let it run through the circuit. And we measure the currents and the voltages across the parts we care about that we think of as the health metrics. So designing the health metrics is probably the most important part. So from spending time with Jeff perspective, and obviously Avi as he continues to work on a cat model, one of the most important aspects of describing the analytics is actually not about the technical methodology at all. It's about understanding the system model and understanding what is actually the appropriate representation of health. So in the case of this model in front of you, there's 2 metrics that we are actually using that we are constructing to be healthy. One of them is a C-org operational KPI that's based on a maximum likelihood estimator, which is also technically machine learning.
Say that again. C-org.
Operational. I'm just calling it the operational KPI, but what it is, it's a thing that I'm calling a lag gain operator, and it basically says how efficiently it transforms spending money now to making money later. So there's like a lag in time and a multiplication on money. And if that multiplication is bigger than 1, or like if the integral of that multiplication is bigger than 1 in the future, then you're turning spend now into more money in the future. So that we actually are creating this KPI, and technically it's also machine learned because it's a maximum likelihood estimator. There's no exact answer. We're looking at 2 streams, one which is spend and one which is revenue, and we're fitting an operator that says that it's defined as a transformation from spend in the past to revenue in the future. And if we look at how effective that operator is, that's a KPI. It's saying what's the gain? How many dollars do I make per dollar spent, and over what distribution in time? Like how long do I have to wait? Because
so it sounds like for our purposes, layer 2, we like in iteration 4, we do all the work to gather the data and understand the model, understand the system itself. And then layer 2.5 in iteration 5, we take those learnings, we apply machine learning algorithms to the data that we've gathered. Yeah. And
just think of it as leveling it up, because we're just not going to want to get into how and why and what that means, but we will be able to level it up with machine learning, but you only do the machine learning layer stuff after you actually understand what you're doing. Trying to do the machine learning stuff before that is the reason why so many machine learning projects fail.
Yeah. So we don't, but I just need to be able to say that, like, why does someone want us to get to iteration 5? You know?
Because the system it is absolutely a huge lift to have the machine learning. The problem is you can't put the cart ahead of the horse.
Yeah, we got to gather the data so that we can actually perform machine learning on enough data that it will.
We have to 2 things though. We have to gather the data, and we have to gather the understanding. Because learn long problem statement is worse than not using it at all.
So we would be gathering the data in layer 2, but until so they would be continuously gathering the data, but really determining the metrics would happen in iteration 5 in level 2.5.
So let me be honest with you. Most likely, we will be doing quite a bit of metric design in the earlier phases. We don't yet know now what those metrics are, but things that are happening in our real experience with 1, 2, and 3 are going to inform our systemic understanding. So so that's part of the reason why I'm saying there's only so much you can say, because the really light fire under your ass is going to be as we get through 2 and 3 and we really understand what it means for the system to be healthy. The analytics revolve around that.
Okay. But like where we will be determining some of the metrics in layer 2 during the best that we can, and then we will revise the metrics in iteration 5.
I doubt the metrics will be getting revised. I have a feeling that by then, because remember, this is a long arc project and it's pretty well mapped to be like step over step learning things. I would like to think that our understanding of the appropriate health metrics will be pretty mature by the time we're working on 4, because we should have been paying attention to it in 2 and 3. This isn't a concept that's coming in. It's the notion of health KPIs is not going to be new in level 4. The notion of health KPIs needs to be with us the whole time. Yeah. It's one of the most important things. The fact that it won't yet be this, hardcore dashboard analysis machine learning shit is because it takes time to get there. But conceptually, the notion of operational health metrics need to be like hours literally in every 1, 2, 3, 4, 5. You see what I mean? So like I'm not saying like this is going to be like, oh no, let's figure them out in 5. Like we're going to be thinking about this and refining this understanding every step of the way.
Yeah. Okay. Okay. So I feel like we got there. I feel like we have enough to like, I don't know. Do you feel like that? Mm-hmm. I feel like we have enough of an understanding to communicate it to the point of like, whoa, hey, like we don't know enough about this, and honestly, this is all Zargham territory. So,
but I also don't want so what I don't want this to be is a scenario where like we're punting it or not giving it its right attention. The just truth is that this is the kind of thing that cannot, like, you just have to be really careful about the cart and the horse. It's doing it well is a lot more work than people give it credit for, but it is something that this whole thing has been with us. The challenge ends up being like how to marry what I would consider expectations with reality. I'm very comfortable with the reality. It's going to be step over step. We're going to learn what we need to do. We're going to have the skills we need to do it. We have the partners and the contractors we need to do it. We will get it done. What scares me is communicating it, because I'm often in the scenario where I'm trying to communicate things to people that are so far over their heads that trying to communicate it makes it worse. Yeah. And that's what I'm afraid of.
Yeah. Well, we have to tell people something. So I think that's where we are. I think we got there.
Oh, I'm not complaining about you guys. I very much feel like this is a great conversation. By any chance, were you recording it?
We did. We started recording like pretty much. Yeah. I mean, pretty much while you're describing layer 1, which I feel like we all understood.
Yeah, I just figure it'll be helpful. I got to run because I have a call with Max now.
Okay. We'll think on some things later. Ping us if you have a moment. Or
I mean, we're all in Europe now, so it'll be a little easier to schedule time.
Mornings are great.
Mornings are good. I think my next 2 days start blocked off at 10 a.m. though, so I might ping you in the morning because I am going to the Technical University of Munich tomorrow, and I'm meeting with someone from Siemens on Friday, and then I have like my afternoons and evenings are all full. So. Yeah.
Well, we'll see how it works out. But hey, we'll have a lot of time to think next week for sure.
Yeah. And Jeff, just to be clear, the stuff that we're talking about with analytics too is not a bad thing to talk to with Max to the extent you have time with him or if you go to Odessa, because he is very much the partner that I use for the development and UX. And so he's been in the loop on these conversations about CAD for a long time. He was actually at DevCon and was hanging with you. I stayed and we were talking about CAD then.
I mean, I can't tell you what a bonus it is that Max is working on UX for continuous organizations and that you guys are already being paid to like start working on continuous org. That's fucking magical, dude.
Yeah, I walked into Thibaut's office and just started dropping knowledge and got lucky.
Yeah, man, it was a huge score and a huge bonus for Common Stack. So I'm really happy about this.
I mean, I think we all, I mean, back to the whole thing about all sort of, we have so much to do that it's so helpful that we are all kind of finding the places where our, where things are complementary and actually taking advantage of that complementarity rather than people just sort of getting up in arms and competing even when they're not competing.
Yeah, of course, man. It's all cooperation on our side. Okay, well, we'll let you go.
Cool. Thanks.
See you, buddy.
Bye-bye.